Welcome back to the session of My Teacher, the biggest classroom of the UAE. So, we are in the process of discussing the concepts about electromagnetic induction for grade 12. So, I hope all of you are tuned with it, the grade 12 students. Now, it is a live program. So, if you have any queries, any doubts, you can call me from on the number, same number which is displayed on the screen. So, we just finished discussing concepts on self induction, but self induction I will just brief you about that once again. Have a self induction. Okay, we will come back to mutual induction after this. This is we have seen, we compared it with resistor. Resistor R, corresponding equation we have V is equal to IR. Then inductor, corresponding equation we have seen is phi is equal to Li. Unit of resistance is ohms, unit of inductance Henry, right. Then we have seen the equation for resistance, various factors affecting resistance, phi is equal to rho L by A. Similarly, factors affecting inductance, we have seen mu 0 n squared A L. By the way, we wrote mu 0 because the air is considered to be within the solenoid, but if there is a medium, let us say an iron rod is inserted, what change will be there? This equation you may rewrite as L is equal to mu 0 mu R also will come, where mu R is the relative permeability of the medium inside. Okay. Now, another equation, the equation for the similar to that we have seen in capacitor, right, capacitor. So, that way we can say include this also, capacitor is C. What is the equation? Q is equal to CV, resistor, inductor. Okay, we make it like this. Okay, just have a comparison, capacitor, resistor, now inductor. Q is equal to CV is the equation here. Here we have V is equal to IR. Here corresponding equation phi is equal to Li. Unit of capacitance farad, ohm, resistance ohm, Henry, right. And factors affecting capacitance epsilon 0 A by A D. Similar to that, here we have factors affecting resistance rho L by A, inductance mu 0 n squared A L. You see, this is the comparison. Okay, so now one more thing, in a capacitor there is storage of energy, electrostatic energy stored in it, and it is given by an equation half CV squared. This is the energy stored in a capacitor. So, two equations we have studied for capacitor, one is energy, total energy stored, another equation we studied was energy density. You know what is energy density? Energy per unit volume, we will write it as UE. You get the equation half epsilon 0 E squared. These two equations we have seen for capacitors, right. Similar equations even we have for inductor as well. So, how do you get those two equations similar to these two? Okay. So, I will show you. The equation W is equal to QV, based on that we got this equation. Okay. Whereas, the other one, we have the equation we saw, induced EMF E is equal to minus d phi by dt. All right. The magnitude of induced EMF is d phi by dt. All right. Instead of phi, we can even write Li, right. So, L into di by dt, like this you can write L into di by dt. And the equation for energy, the equation we have basically VIT, that is the equation for electrical energy. Okay, we will write the letter U to represent energy. Right. So, in the place of V is if you take it as induced voltage, this is induced voltage, you will write it as L di by dt. By the way, this equation, when an inductor is connected to a circuit, connected to a battery, the current will not abruptly come to maximum, it will gradually only go to maximum. So, to get the total energy in the inductor, we need to integrate it within the first for a short interval of time dt, then you have to integrate it to get the total. So, integral of this V I wrote V is L di by dt into I dt. So, we get the equation total energy is integral L you may take out because it is a constant, I di I di when you integrate, the limit should be from 0 current to maximum current, let it be I. So, what will be the, after integrating we get this is I squared by 2 integrated result, I squared by 2 into L, this is what we write as half Li squared. So, this is the equation similar to what, half CV squared in capacitor, here we have half Li squared in inductor. This is the expression for energy stored in an inductor. So, I think you made a note on this. This is what is required for getting the expression for energy stored in an inductor. Now, similar equation in capacitor is half CV squared. Same way, here we have another equation, that is energy density. Now, energy density, when you say energy density in a solenoid, that is total energy divided by total volume. Total energy, we have the equation half Li squared, we just now we derived the equation, divided by volume of the inductor is area into length, this volume, right. Half, instead of L we derived the equation mu 0 n squared Al divided by Al into I squared. But one equation we know, for magnetic field B is equal to mu 0 Ni. So, what will be I then? I is equal to B by mu 0 n. That way we can write it over here, instead of I squared is what, B squared by mu 0 squared n squared. Okay, on solving this, one mu 0 is cut, right, n squared is cancelled, Al cancelled. So, finally we get B squared by, even one mu 0 is gone, B squared by 2 mu 0. This is the energy density. So, in similar to this, we have seen an equation in capacitor, half epsilon 0 E squared. You can make out one thing clearly, the energy density in capacitor, right, it is directly proportional to E squared. Similarly, energy density in inductor is directly proportional to B squared. So, either in capacitor or in inductor, both the cases, the energy density is directly proportional to square of the field, either electric field or magnetic field. Okay, so what all, just let's have a quick recap on what we have done. Self induction, inducing EMF in a coil due to the change in flux in the same coil itself, and it is measured by a quantity called self inductance or simply inductance, given by the equation mu 0 n squared Al, and that means self inductance of a coil depends on those old factors. And further we can say it can also be used as an inductor, or it's also sometimes referred to as a choke coil, choke coil in a circuit, which will be used to reduce current in circuits like AC circuits, wherever there is a change already there. By nature the current is changing, then only we can use such a device for opposing current. So, instead of resistor we can use inductor, we can prefer that, because without reducing the energy, without loss of energy, we would be able to oppose current in the circuit. Then we could see the expression for energy stored, energy density as well, right. Same way we have another concept, that is what we call as mutual induction. That is, just think of this aspect like one coil, okay, close to that another coil, so they are insulated from each other, because there is no contact. But the thing is, there is an there is a galvanometer here, and there is a battery here and a key. So, what you will observe is, the moment the key is closed, suddenly the EMF will be, you will see a deflection. Once again, the moment you close the key, you see there is a deflection in the galvanometer. Galvanometer deflection means there is a current means there is an EMF induced, but that EMF to induce, the change in flux is developed due to the current in the other coil, neighboring coil. So, mutual induction is what, inducing EMF in one due to the change in flux developed in the other coil. Right, you might have heard of the term passive smoking. If you say in lift and all, it is not at all, it is a crime to smoke inside a lift. Why? Because it is like passive, you are you are doing something, because of that the effect is on others, right. This is what is happening, mutual induction, change is made by one coil, right, whereas the other one, there is a change, there is an EMF induced in the neighboring coil. So, phenomenon of inducing EMF in a coil due to the change in flux developed in the neighboring coil is what is called mutual induction, right. So, they are similar to the other one, we have the equation like phi is equal to Mi, M is called mutual inductance, unit is Henry gain, and between two coils, have a look at the diagram. So, on the screen you look at, there are two coils kept like that, you might have seen the diagram. Yes, two coils of radii R1 and R2. Okay. So, between them the total, you may, all of you may refer the textbook to see a derivation related to this, the expression for mutual inductance between the two coils. We may get the equation, it is also an important equation similar to the other derivation. It is given by mu 0 n1 n2 pi, the small radius is R1, right, mu 0 n1 n2 pi R1 squared, okay, L. This is the equation we have for the mutual inductance of two setup of that sort, a setup of two coils like that, or two solenoids in that way, all right. This is an important derivation, and what I will explain now is, where do we make use of this? This is very much used in transformers. So, it is a very important concept about learning concepts about transformers. You know, transformer, you might have seen transformers in many places. Where do we exactly use transformers? In day to day life, we use transformers, where we use in, the mobile phone charger is there, no, charger, or we say adapter. Okay. That mobile phone charger is basically a transformer. So, what does the charger do? A mobile phone, you are charging your mobile phone. What does the charger do? See, why we are not able to straight away connect the mobile phone to the socket without the help of the adapter or the charger, because the voltage available is 230 volt, all right, but what we require maybe in a mobile phone 6 volt or 9 volt we need. So, from 230 volt should be reduced to 6 volt or 9 volt according to the requirement. So, this is what is done by a transformer. So, transformer is reducing the high voltage to low voltage. So, in a mobile phone charger we are using a transformer. Is that clear? There is one more process, that is conversion of AC into DC, that also is happening, that we will discuss in another chapter, but here we have to focus on reducing voltage. So, wherever you want to reduce voltage we can use transformers, all right. That is why, like in normal radios, tapes, tape recorders and all, we have we operate with batteries, we can operate with batteries, but in the voltage that required is not 230 volt, but we are making use of this volt with the help of a transformer, we reduce it, right. But at the same time, you might have seen in there are big transformers, have you seen in substations. In many areas like near what is in Sharjah, Dubai and all, you might have seen many substations. Near the residential areas you can see the title substation. What is that? What do they do? They are reducing the voltage to the required volt for the houses, because you might have seen, just have a look at the picture, look at the screen. You know the transmission lines, you are well familiar with these lines. If you look at the industrial areas and all, you can see the big transmission towers. What do they do? What the transmission was? What's the purpose of these transmission lines? They are actually carrying electrical power from where? From power stations to a distant place. So, electrical energy is generated in a power station, which is being carried away to the distant places with the help of these transmission lines. Why it is at a big height, and why it is not usually taken through the dense populated area? It is usually through industrial areas where people are not staying, or through remote places they are used. Why? Because they are sent from power stations, they are sent to distant places at a very high voltage. Now, the question, why should we send it at a high voltage? Okay, now listen, I will explain. Now, what I am going to explain is why electrical power to be transmitted to a distant place at a very high voltage. Why we need only 230 volt. Okay, electrical what is a generator in a power station produces electricity. Say suppose this is a power station. In a power station, electrical power is generated from a generator, but straight away we cannot send it to if you send, say these are the transmission lines. So, this is the power station, I will write it as PS, power station. This is the town where we are staying, there are so many houses, factories and all, they require electrical energy. It is to be transmitted from this to that. For that purpose only these transmission lines are used. Okay. So, now what happens is, if you are sending it like this, in this way through transmission lines, lot of energy would be wasted in the form of heat. You know, do you remember the equation for the power loss in a resistor? The equation we have is I squared R, P is equal to I squared R. You might have studied this. This is the power loss equation. So, we see that depending upon the amount of current passing, depending upon the resistance of the transmission lines, we can calculate the amount of power lost in transmission lines. Again, remember, what I am going to explain is an important point: why do we require a very high voltage for sending electric power to a distant place? That is why, you know, in those lines are sometimes referred to as 11 kV lines. You know, in India there are so many 11 kV lines. 11 kV means 11,000 volts. So, the electric power is sent at 11,000 volt, such a very high. That is why it is very extremely dangerous. That is why it is at a very high, big height. All right, and it is extremely dangerous because very high volt, right. So, 11,000, but in the 11,000 volt, same volt, we cannot send it to the houses straight away. That is why we are using substations. So, from electric power, the electric power from the power stations through the transmission lines will reach the substation, which is in a town. So, in the substation from 11,000, it will be reduced to the required voltage, maybe 230 volt. Then it will be distributed to houses. Again, we did not answer the question, why do we require such a high volt? Listen, this is power loss. Okay. So, we want minimum resistance or minimum current, then only power loss can be minimized. You know, remember, for the major loss of energy in the form of heat is what is generally called transmission loss. That is mainly due to the resistance of the wire. So, as far as possible, we have to keep the resistance of the transmission lines minimum. Okay, that is one factor. So, that beginning itself we should take into account. So, we have to select a material which has got a very low resistance, then only power loss can be minimized. So, while transmitting electric power, because you know, it is very a large amount of energy is transmitted. Okay, you know, there will be a big loss if we are not trying to minimize the energy loss during the transmission. Okay, so first of all, resistance. You know, copper has a very low resistance, but still we do not prefer copper over here because of two reasons. One is, copper is, you know, we want large quantities, it is more expensive. Not only that, it is heavy. So, if it is heavy, what happens is, you know, we have seen these transmission lines. If it is heavy, then it will sag, no, it will not, we will need so many towers like that. Alright. So, it should not be, therefore, we are not using copper, instead which is the next possible material is aluminum. So, aluminum is the most preferred material for transmitting electric power because it is light and is of low resistance. Okay. Anyway, it has some resistance. So, now the major aspect to understand is what? I, current, to keep the current as minimum as possible. How do you keep the current minimum? Again, you come back to the power station. In power station, electric power is generated with the help of a generator, and it is given by the equation P is equal to VI. This is the power delivered from a source. For a given source, power is a constant. So, what we do is, after coming out of the generator, we will send it to a what we call as transformer. This is the role of the transformer here. Okay, so it will be sent to the transformer. This transformer will, what does it do? It will increase the voltage to very high value. That is called stepping up. Okay, what we have seen in the case of the mobile phone charger, what do we do is reducing the voltage. So, we are stepping it down. So, the transformer used over there is step down transformer, but the transformer which we use over here in the power stations is step up transformer, increasing the voltage to very high value. So, what is the purpose of this? If you increase the voltage, that is why 11,000 volt, when we increase the voltage to very high value, what happens? Current will be considerably reduced, because power of a source is a constant, power of the generator is a constant. Alright. So, increase the voltage to very high value, which will reduce the current to very low value. The current when reduced, what happens? The power loss also will be minimized. So, it is so simple. So, we prefer the material which has got a very low resistance. That is one thing, one way it is minimized. But further, by increasing the voltage to a very high value with the help of a step up transformer, we are reducing the current, thereby we are reducing the power loss. So, the basic role of a transformer in electrical transmission is to minimize the power loss. But one thing is, in power station we are increasing the voltage, but when it comes to the town, there we are using in a substation, we are using a transformer called step down transformer. So, the transformers which you have seen, you look at the screen, just have a look at the screen. So, this is what I said, this is a transformer, you might have seen it is very common, you can see it in the power stations, okay, in the power stations or substations we call. You can see the transformers of this sort, this is the basic mechanism of the transmission, and this is the structure of a transformer which we will discuss on a later stage. But now come to this once again, you listen to the board. Once again let me tell you the mechanism, this alone can be asked as a question, the mechanism of the transmission of electric power from power station to a distant place. Once again, in a power station, electrical energy is generated using a generator which will be sent to a step up transformer, in which the voltage will be increased to a very high value, due to which the current will be reduced. With the low current, high volt, it is transmitted, all right, through the transmission lines. So, the current, since the current is very low, the power loss also is minimized. So, in such a high voltage, the current is coming to the town. Okay, in the town it reaches a substation. In the substation, the current, the voltage should be made to reduced. Otherwise, we want the normal voltage. Normal voltage means maybe if it is coming in 11,000 volt, it should be reduced to 230 volt, for which we will use a step down transformer. So, during transmission of electric power from power station to distant places, we use both step up transformers and step down transformers. So, the ones which we see in our town in substations is what kind of transformer they are? They are step down transformers, whereas the ones which we see in power stations, they are step up transformers. All right. So, transformers make use of the phenomenon what we call as mutual induction. The phenomenon of mutual induction is what is made use of in step up and step down transformers. So, transformer is another very important concept. So, the time does not permit us to discuss more on the transformer, more questions and all we will be able to discuss on a later stage. But anyway, all of you make it a note that the My Teacher program is going to have a pause today, and after the vacation, when you come back after vacation, we will resume with the classes. You enjoy your holidays. At the same time, the senior classes, 11th and 12th students, the main focus should be to rectify your problems, what all you had to do. After the examinations, you came to know where all you went down, where all you failed. You rectify them, and after the vacation when you come, you should be completely refreshed, and there should not be any black marks on your performance. And let us hope for the best, and again happy holidays, enjoy your vacation. We will see again with another topic after the vacation. Till then, bye bye.